All right, welcome to the deep dive. Today, we're going to be really getting into something that's super fundamental to how we think about science. Like how do we decide if a scientific idea is actually, good or not? And I think a lot of times it comes down to, is it better if a theory predicts something totally new or if it just explains something we already knew? So we're talking about like prediction versus accommodation. With prediction, you see some consequence of your idea like out there in the world after you've had the idea. But with accommodation, it's more like your idea fits facts that were already known, like when you first came up with it.
Right. And that leads to a really interesting question. Does one of these types of success actually give us like a better reason to, to trust a scientific theory? The idea that prediction is somehow like stronger, that's often called predictivism. Yeah. And honestly, this whole debate is something philosophers of science have been going back and forth on for ages.
Yeah, totally. And I know some people listening might be like, okay, but why does this even matter? But think about it. Every time you hear about some big scientific breakthrough, the fact that it predicted something new, something no one knew about before, that's often seen as the ultimate, like, proof. But is that really justified? That's what we're going to explore today. And honestly, getting into all the different views on this can really challenge some of those, like, gut feelings we have, and it gets surprisingly complex.
It definitely does. This whole discussion has roots going way back, like to the 1700s and 1800s, when people were really starting to grapple with, the scientific, what they call the method of hypothesis. And back then, there was this real concern that like scientists could just keep changing their theories to fit whatever new observations came up. And if you could always tweak it to fit the data, could you ever really, test it properly?
Right. It's like having this theory that's always right no matter what, because you can always come up with some excuse as to why it fits. But then you had thinkers like John Herschel and William Whewell, and they were like, no, a theory's got to do more than just explain what we already see. They argued that, like, the real test was prediction, boldly predicting something totally new and unexpected.
And Whewell really nailed it when he said that, if a theory can predict a surprising result, something no one saw coming, that gives it a special kind of authority. Like it suggests that it's genuinely tapping into, how the world works, not just being clever with existing knowledge.
But of course, not everyone was on board with this. Like John Stuart Mill, he famously disagreed with Whewell, and he was really skeptical. He even said that, like, being so impressed by predictions, that was kind of for the ignorant vulgar, as if serious scientists shouldn't get so excited just because a prediction came true.
It's a good point. Like, is the success of a prediction really a sign of a theory's strength, or could it just be a lucky guess? John Maynard Keynes later came along, and he had a more, nuanced take on this. He actually thought this idea of, prediction having the special power, he thought it might be an illusion.
An illusion, really. What was Keynes getting at there?
Well, he was suggesting that the real strength of any hypothesis, any scientific idea, comes from whether there was already, good reason to believe it before you even looked at the evidence. Like, if there's strong support for the idea beforehand, what he called a priori knowledge, then it's already more credible, right? So any prediction that comes from that well-supported idea, it carries weight because of that foundation. But if a prediction just comes from some, wild guess, then even if it turns out to be right, it doesn't mean the idea behind it suddenly becomes, strong.
So it's not just about the timing, like whether the prediction came before the evidence, but it's about the quality of the idea itself beforehand.
Exactly. And Keynes really felt that a lot of the time we just give extra credit to predictions because they happen to come first without really noticing all the, the good reasoning that might have been there behind the scenes. He thought this idea of predictivism kind of hid that underlying support.
That's really interesting, and this kind of sets the stage, I think, for Karl Popper. He was really focused on, what even makes a theory scientific in the first place.
Oh, absolutely. And a big part of Popper's work was trying to draw that line between real science and, what he called pseudoscience. Like theories that seem to explain everything, but they never actually put themselves at risk of being, wrong. He called this the demarcation problem.
And his answer was all about, falsifiability, right?
Exactly. Popper's big point was that a genuine scientific theory, it has to be testable, and it has to actually be possible to prove it false. He thought that pseudosciences were just too flexible, too malleable. They could always be adjusted after the fact to fit whatever new evidence came up, so they were like impossible to actually contradict.
Right. Like if my theory is that all swans are white, the first time I see a black swan, I just say, oh, well, that's not really a swan. It's just a way of avoiding, being proven wrong.
Precisely.
Hmm.
But real scientific theories, they make specific, risky predictions. They kind of stick their neck out, because if those predictions don't pan out, then the theory's in trouble. And he always used the example of Einstein's theory of relativity,
Mhm.
which made these really bold predictions, like, that light actually bends. And that could have been shown to be false.
So for Popper, it wasn't really about whether a prediction was successful, but that the theory actually made those risky predictions in the first place.
Yeah, that's a crucial point. For Popper, the act of making a prediction, putting your theory out there, risking that it might be wrong, that's what made it scientific. It's about, like, a willingness to be wrong. And that's a bit different from, say, Wilwell and Herschel, who really saw successful prediction as, like, the hallmark of a good theory. But Popper, he was super critical of this whole idea of induction. That we can actually prove a theory true by just, like, making more and more observations. So for him, science was about constantly testing theories. And the ones that survived, well, those are the ones we kind of tentatively accept. But if we can never really confirm a theory, what does it even mean when a theory does predict something successfully?
Right. It's like, it sounds like he was more interested in the process of science, the way it works through prediction, rather than using prediction as like a direct measure of whether a theory's true.
Yeah, exactly. And building on Popper's ideas, you have Emre Lakatos, who developed this idea of scientific research programs, which is kind of a more, detailed way of looking at how these scientific ideas, develop and compete over time.
So not just individual theories, but like broader frameworks of ideas.
Right. And for Lakatos, a research program, it has this hardcore, these fundamental assumptions that the scientists within that program, they don't abandon. And then around that, there's this protective belt of other hypotheses and ideas that can be, changed or replaced as new evidence comes in without, rejecting those core ideas.
So if some new observation, seems to go against that hardcore, they don't throw everything out, they adjust the protective belt instead.
That's the idea. And then Lakatos came up with these concepts of, like, theoretically progressive and empirically progressive research programs. So a program is theoretically progressive if it keeps coming up with new theories that predict genuinely new facts, things we didn't know before. And it's empirically progressive if at least some of those new predictions actually get confirmed, they turn out to be right.
And this was Lakata's way of like judging whether a whole scientific approach was, on the right track.
Right. He thought a program was in trouble if it stopped being theoretically progressive, if it wasn't leading to new testable predictions. And for him, science was really this competition between different research programs, where the ones that kept making and verifying those novel predictions, those were the ones that were, advancing knowledge.
That makes a lot of sense. And this brings us to the idea of ad hoc hypotheses, which seems to be like a big red flag in this whole discussion, right?
Yeah, for sure. So in everyday talk, ad hoc just means something created for a specific purpose, like on the spot. But in science, especially when we're talking about this preference for prediction, an ad hoc hypothesis is often seen as, suspicious. It's like you're adding something to your theory just to explain away some problem, some anomaly. And a lot of times it feels like you're just protecting your theory from being, falsified.
So it's like adding a patch to your theory at the last minute just to make it fit.
Exactly. And Popper really had a problem with ad hoc hypotheses because, often they couldn't be tested independently. Like, if the only reason you have to believe in this new part of your theory is that it explains this one specific problem, but it doesn't make any other predictions you can actually go and check. Well, that's ad hoc in a way that Popper found, problematic. He worried it could make theories immune to, like, real testing.
But it sounds like, the meaning of ad hoc itself has gotten more nuanced over time.
Yeah, it has. Later philosophers pointed out that there are, different ways a hypothesis could be ad hoc. For example, Elie Zahar talked about, like, a hypothesis that doesn't lead to any new observable consequences. He called that ad hoc 1. Or one where its new predictions haven't actually been checked out yet, ad hoc 2. Or one that just doesn't really fit with the, the core ideas or heuristic of the broader research program it's part of, ad hoc 3.
So even if it makes a new prediction, if it seems kind of disconnected from the main ideas of the theory, or if it hasn't actually been tested yet, that can still be a red flag.
Right. And then there's the idea that sometimes needing an ad hoc hypothesis might be a sign that there's a deeper problem with your theory. Like, maybe you need to revise the whole thing, not just add a little fix. Our source mentions how Einstein saw the Lorentz-Fitzgerald contraction as an ad hoc addition to the ether theory. And the idea of the neutrino, when it was first proposed by Pauli, that was seen as a pretty ad hoc way to solve a problem in quantum mechanics.
It's amazing, right? The neutrino, which turned out to be, like, fundamental to physics, some people thought it was just a patch at first.
Yeah, it just goes to show you that how we judge whether a hypothesis is ad hoc, that can change as our understanding of things grows.
Yeah.
And there's also, like, a degree of subjective judgment involved, right?
Right.
One scientist might see an elegant solution where another sees a clumsy fix. So some philosophers have even argued that maybe we can't have a totally objective definition of what even counts as, a bad ad hoc hypothesis.
So we've got this idea that prediction is better, and we're wary of ad hoc explanations. But what does it even mean for a prediction to be novel? It can't just be something that happens in the future, right?
No, definitely not. The whole idea of novelty is way more complex than it might seem at first. The first attempt was this temporal condition of novelty, which just said a prediction is novel if the fact it predicts wasn't known when the theory was made.
Right, that seems simple enough. What's wrong with that?
Well, the problem is that it makes the importance of a prediction depend on, just when something happened to be discovered. Like, imagine a theory that explains some really fundamental phenomenon beautifully, but someone else just happened to stumble on that phenomenon before the theory was proposed. That shouldn't make the theory any less powerful, right?
Yeah, totally. It feels like the connection between the theory and the fact, that's what matters, not just who knew what when. So, what other ways have philosophers defined novelty?
Well, one big one is what Zahar called problem novelty.
Yeah.
So a fact is problem novel for a theory if it wasn't part of the specific problem that the theory was created to solve. Like Einstein's theory of general relativity wasn't made to explain the weird way Mercury orbits, but it ended up explaining it perfectly. So that explanation was problem novel.
And then there's this idea of use novelty, right?
Yeah, that one was distinguished by Gardner. And it basically says that evidence is use novel for a theory if that specific evidence wasn't actually used by the person who came up with the theory, even if it was known at the time or part of the problem they were trying to solve. This is related to the heuristic conception of novelty, which focuses on what was going on in the scientist's head. Like, if a piece of data didn't guide the development of the theory, then successfully predicting that data is seen as heuristically novel.
But that sounds like it depends on, knowing what the scientist was thinking, what they knew, how they came up with their ideas. That seems pretty, like, subjective, doesn't it?
Oh, for sure. And that's a big point of controversy. Some philosophers, like Leplin, argue that the strength of a theory shouldn't hinge on, the scientist's private thoughts and intentions. Like, how can we objectively evaluate a theory if its support depends on something we can't even see?
That makes sense. Are there, like, more objective ways to think about novelty?
There are. Another approach focuses on competing theories. So the idea is a prediction from theory A is novel if it's not also a consequence of, the best rival theory we have at the time. Like relativity's prediction of the way Mercury's orbit shifts, that was novel because Newtonian mechanics, which is the big theory at the time, it couldn't explain it.
And then their ideas of novelty based on those research programs that Lakatos was talking about, right?
Exactly. Thinkers working within that framework, like Frankel and Noonan, they came up with definitions of novelty based on, whether a fact had already been used to support theories in the same research program or whether it could easily be accommodated by a competing one. But the important thing to remember is a single piece of evidence can be novel in a bunch of different ways. And some types of novelty might be seen as stronger support for a theory than others.
So we've got all these different ways of defining novelty. Does that mean there are also different ways of thinking about, predictivism itself?
Oh, absolutely. And that leads us to what you might call a taxonomy of predictivism. So there's global predictivism, which says predictions are always better than accommodations. And then there's local predictivism, which says prediction is only better in certain situations. Then you have strong predictivism, which says prediction is just inherently more valuable, period. And weak predictivism says that predictive success matters because it often points to other, good things about a theory. And you can imagine all these distinctions, they can overlap and intersect with all those different types of novelty we've been talking about.
This is getting pretty complex, huh? Okay, let's move on to this idea of the null support thesis. What's that all about?
Okay, so the null support thesis is like a really hardcore version of predictivism. It says that a theory gets zero actual support from any evidence that was used to, build the theory or fine-tune it.
Yeah.
It's like if you tailor-made your theory to fit existing data, the data never really had a chance to prove you wrong. And this idea, you can find versions of it in the work of Bacon, Descartes, Popper, Lakatos.
It's like if I perfectly match my story to what a witness says, that doesn't mean my story's true. I made it that way on purpose.
Exactly. Gier argued that if facts are used to actually construct a hypothesis, then the fact that the hypothesis fits those facts, well, that doesn't give you any independent reason to believe it. The worry is that, the very act of making the theory fit the data kind of builds in a protection against being wrong about that data.
But it sounds like there are some, counter arguments to this idea.
Oh, yeah. Howson, for one, argued that once you've actually stated a hypothesis, well, it either matches the facts or it doesn't. This idea that a fact had no chance to disprove a specific fixed hypothesis, that's not so clear. He used examples to show how even data that's used to refine a hypothesis can still provide support for it, especially if we really understand the underlying processes, that are generating that data.
And this all connects to Bayesian statistics and this thing called the problem of old evidence.
It does. So, standard Bayesian reasoning, it kind of suggests that if you already know a piece of evidence is true, then learning that a theory explains it, well, that doesn't necessarily make you more confident in the theory. And this seemed to support, the null support thesis. But then Howson and others came along and said, hold on, we can deal with this by looking at what our probabilities would have been if we didn't already know the evidence. And that kicked off a whole bunch of debate within Bayesianism about how to properly handle evidence that was known before a theory was even proposed.
Okay, so it sounds like the null support thesis, it's got its problems. Let's get into some of the more, modern ideas about predictivism, starting with this reliable discovery methods idea from Maher.
All right, so Maher came up with this really cool thought experiment involving coin flips. Imagine two scenarios. In one, someone watches 99 coin flips, and then they predict the 100th one correctly. In the other, someone predicts all 100 flips in advance, and then the first 99 turn out to be, right. Now, most people, they have this intuition that, like, the person who predicted all 100, their prediction for the final flip is somehow, more believable.
Yeah, I get that. It's like it makes you think they must have some kind of, understanding of how the coin is flipping.
Right. And Maher used Bayesian analysis to argue that those first 99 successful predictions, they actually provide evidence that this person has a reliable method for predicting coin flips. The person who just, accommodated those first 99, their success doesn't give us the same reason to think they have a reliable method.
So it's not just about getting the prediction right, but it's about what that success tells us about the way the prediction was made.
Exactly. And what Maher's work suggests is that a lot of times, successful prediction is a sign that the theory behind it, it might be based on a reliable way of, understanding the world. This is all in line with a weak form of heuristic predictivism.
Okay, that makes sense. And then there's Lipton's fudging explanation. What's that one all about?
So Lipton's argument was that when scientists are trying to, accommodate existing data, they might be tempted to fudge their hypotheses, like tweaking them in ways that are kind of artificial or inelegant just to make them fit the facts, even if those tweaks don't really make sense, with the core of the theory or with what we know about science in general. He used this example of the phlogiston theory, where they had to say that phlogiston had negative weight to explain some experiments, which just clashed with, basic ideas about what weight is.
So the idea is if you're predicting something brand new, you're less likely to have to make these weird ad hoc adjustments.
Right. The theory kind of has to stand on its own 2 feet to make that prediction. And then Lipton raises this interesting question. Are scientists even aware of this temptation to fudge? And could there be a difference between, like, how much a scientist thinks an accommodated hypothesis is supported and how much support it actually has objectively?
Okay, that's a good one. Now we come to Lange's idea about arbitrary and non-arbitrary conjunctions. And that sounds pretty abstract.
It is, a little bit. So Lange, he revisited that coin flip example we talked about before, but he added a twist. He imagined those first 99 flips being in a very specific alternating pattern, like heads, tails. In that case, our intuition that the predictor's prediction for the 100th flip is somehow better, well, that starts to fade away.
Why would that specific pattern, change our intuition?
So Lange's argument uses this idea from Nelson Goodman called an arbitrary conjunction. It's basically a statement where the different parts don't seem to have any, real connection to each other, like the sky is blue and my socks don't match. In Maher's original example with the random sequence, we kind of suspect that the sequence of coin flips is just, a bunch of random outcomes. So even if someone gets those first 99 right, it doesn't really tell us anything meaningful about the 100th. But when someone predicts a random sequence correctly, it makes us think maybe there's some reason, some pattern behind it. But with that alternating sequence, even if someone predicts it right, it still just seems like a specific, maybe even arbitrary pattern.
So the power of prediction, maybe it comes from making us think that the connection between the theory and the evidence isn't just some random coincidence.
Yeah, that's the idea. Lange thinks that in science, accommodating known evidence can sometimes lead to theories that are like those arbitrary conjunctions. They fit the data, but they don't really show us any deep underlying connection. And for him, the difference between prediction and accommodation is that prediction tends to, avoid those arbitrary conjunctions, while accommodation tends to, lead to them.
Sure.
So that's why prediction seems better. He sees this as a kind of weak heuristic predictivism, where the advantage of prediction is that it's less likely to be, an arbitrary conjunction.
Okay, that's really interesting. Now, Deborah Mayo, she focuses on this idea of severe tests. How does she approach this whole debate?
So Mayo argues that our intuition that prediction is better, it comes from this idea that novel predictions, they give us these really severe tests of a theory. And a severe test, for her, is one that, like a wrong theory, would be very unlikely to pass. So you can see why a prediction about something we haven't observed yet, that seems like a really tough test, right? But Mayo's point is that just because a hypothesis was built to fit existing evidence, that doesn't automatically mean it hasn't passed a severe test.
And she uses that example with the SAT scores, right?
Yep. So imagine we take a bunch of SAT scores, we calculate the average, and then we propose the hypothesis. Okay, the average SAT score for this group is this number we just calculated. Obviously, that hypothesis was made to fit the data. But Mayo says it still passed a really severe test, because if the actual average was different, our hypothesis would almost certainly be wrong. So being built to fit the data doesn't always mean a lack of severity.
Okay, that's a good point. And what about her take on the Eddington eclipse experiment? That's often cited as a big win for prediction, right? It confirmed Einstein's relativity.
Right. So Mayo points out that there was some early data from that experiment that didn't actually line up with Einstein's predictions. But later they figured out that the instruments were messed up, so they threw out that data. And what Mayo says is that dismissing that weird data, based on good reasons to think the mirror was faulty, that was a legitimate part of a severe test, not just some ad hoc way to save Einstein's theory. She says we shouldn't just, dismiss all hypotheses that were made to fit the data because there's a difference between, legitimate cases and problematic ones. But she does agree with this statistical principle that you shouldn't come up with your hypothesis after you've already looked at the data.
Okay, makes sense. John Worrell, he's been thinking about this for a long time, especially through his ideas about conditional and unconditional confirmation. How does he view this whole prediction versus accommodation thing?
So Worrell's view is pretty complex, and it builds on this Duhemian idea that scientific theories, they're not just one big claim. They've got this core set of ideas,
Yeah.
plus all these auxiliary assumptions, and a lot of those have, like, adjustable parameters. And his argument is that when you use evidence to set the values of those parameters, well, the support that evidence gives you is only conditional. Like, it only supports that specific version of the theory, and it depends on you having other reasons to believe in the core ideas.
And prediction gives you a stronger type of confirmation.
Exactly. So for Worrell, predicted evidence is evidence that wasn't used to, adjust those parameters.
Yeah.
And he talks about two types of prediction that can lead to unconditional confirmation. The first is when a consequence follows directly from the core theory, plus some, very general auxiliary assumptions that we already have good reasons to believe, like, the Copernican prediction that planets would sometimes appear to move backwards. That's an example. The second type is when you have a very specific version of the theory where the parameters have already been set by some totally separate set of data, and then that version successfully predicts a new phenomenon.
So for Worrell, it all comes down to whether the evidence was actually needed to build the theory in the form that made the prediction, not just whether it was known beforehand.
Yeah, exactly. He emphasizes what he calls essential use novelty. It's about whether that evidence was fundamentally necessary. And he thinks this heuristic distinction between prediction and accommodation, a lot of times it's a pretty good indicator of this deeper, logical relationship. So he's a proponent of weak heuristic predictivism. And he actually goes into the case of Mendeleev's periodic table, that arrangement of elements, as a good example that supports his views.
Interesting. Roger White, he has this cool idea called the Archer analogy. What's that all about?
So White's argument focuses on this fact that when a scientist comes up with a theory, they're picking one theory out of, a gazillion possibilities, and it just so happens to entail this specific piece of data. And he says there are two ways to explain this. Either the scientists designed the theory to fit the data, so it was accommodated, or their way of choosing theories is generally reliable, and that's why they ended up with a theory that fits the data. And what he argues is that if we assume the scientists didn't design the theory to fit the data, so it was a prediction, then the fact that it does fit, that gives us evidence that their method for picking theories is probably reliable. But if we assume they did design it to fit, well, then that fit doesn't really tell us much about their method in general.
So he sees this as a pretty strong argument in favor of heuristic predictivism.
Yeah, he does, because he says even if we knew everything the scientists knew, all the background knowledge and evidence, the advantage of prediction wouldn't go away completely, because we can't ever fully know or prove, how reliable our methods for coming up with theories actually are. So successful prediction, for White, it gives us extra confidence in those underlying methods.
Okay, that makes sense. Hitchcock and Sober, they take a bit of a different approach. They look at predictivism through this thing called the Akaike approach, which has to do with the risk of like overfitting the data.
Right. So their argument for weak heuristic predictivism, it's all about this idea that when you build a theory to fit data that's kind of messy and noisy, you risk overfitting. That means you create a theory that it captures the real signal in the data, but it also fits all the random noise. And if you develop a theory without even knowing the data it's going to predict, well, then you don't have that same worry about overfitting.
Right. So it's like finding that balance between how well a theory fits the data and how simple it is.
Exactly. So there's this thing called Akaike's Information Criterion, AIC, and it's basically a statistical measure that tries to balance those two things: how good the fit is and how complex the model is. And overfitting usually happens with more complex models. So Hitchcock and Sober, they use these hypothetical examples to suggest that if you have two theories with similar AIC scores, then maybe it doesn't matter so much whether one was a prediction and the other was an accommodation. But in situations where we don't know the theories or how they are made, a successful prediction might be a sign that the theory has a better AIC score, because it's less likely to have been overfit. But they do stress that they're arguing for a local form of predictivism, and they're not saying anything about, how often these different situations happen in real science.
Okay, lots of nuance there. And finally, we come to Barnes, who brings in this idea of endorsement novelty and the social side of science. How does that fit into all of this?
So Barnes, he talks about epistemic pluralism, which is this idea that when we're evaluating a theory, we should take into account what other, knowledgeable scientists think about their endorsements. He moves away from that heuristic conception of novelty, which was all about how a theory was made, and he focuses instead on, the basis for why people accept a theory.
And this endorsement novelty, it's basically about whether the reasons for believing a theory, whether they include the specific evidence we're talking about.
Yeah. So a consequence of a theory is novel for a scientist if their reasons for endorsing that theory didn't depend on actually observing that consequence. And Barnes argues that this can explain why prediction seems so compelling, because it suggests that the person making the prediction, they had other reasons, other beliefs that supported the theory before the prediction came true. So the successful prediction, it kind of reinforces those reasons. And he even uses some, thought experiments based on Bayesian statistics to support this idea of what he calls virtuous predictivism. He also talks about how maybe our suspicion of accommodated evidence is linked to this worry that scientists might feel pressured to, fudge their theories to fit what everyone already believes. And he goes back to the Mendeleev case and looks at who endorsed the periodic table and why.
Okay, so we've gone through a whole bunch of arguments in favor of predictivism. Are there any, opposing views, any anti-predictivism out there?
Of course. We started with Keynes, way back at the beginning, and his skepticism that the apparent strength of a prediction often boils down to, the reasons we already had for believing the theory in the first place. Howson kind of echoed this later on, using the idea of competing explanations and different initial probabilities, arguing that, a predicted outcome isn't always more supportive than an accommodated one. But these arguments are mostly aimed at the strong forms of predictivism.
Right. What about the weaker forms that we've been talking about?
Well, some philosophers, like Collins, they don't completely reject predictivism, but they argue against the strong heuristic versions. They say that just knowing whether some evidence was predicted or accommodated, that can still give us useful information about a theory. And then you have others, like Harker, who think we should maybe move beyond predictivism as the central focus in these debates about how theories get confirmed, while still recognizing that some of those weak predictivist claims might hold true. Interestingly, even White himself has said that, weak predictivism, it's generally not that controversial.
Okay, so there's a range of views there. What does the history of science actually tell us about all this?
Well, there's this historian, Stephen Brush, who's done a lot of work arguing that this idea that temporally novel predictions are always more convincing, it doesn't really hold up when you look at how science has actually developed.
Yeah.
He uses examples like the bending of light, the way theories about space plasma got accepted, the Big Bang model, things like that, although he does see things differently when it comes to Mendeleev's periodic law,
Hmm.
and of course, Seri and Weizsäcker.